Hi everyone, welcome to today's session. In this session, we will introduce you to the importance of staying critical to your model. The importance of this principle is well described by this quote from Richard Feynman. The first principle is that you must not fool yourself, and you are the easiest person to fool. The idea behind this principle is to validate your model at each stage against available data and list the assumptions you have made during the modeling process. Let's look at an example. In the financial sector, investors can have confirmation bias, which leads them to disproportionately weigh information that confirms their existing investment choices while disregarding information that contradicts them. For instance, during the dot-com bubble of the late 1990s, many investors continued to buy tech stocks despite numerous warnings and indicators of overvaluation, focusing instead on the success stories and optimistic projections. The eventual market correction in the early 2000s resulted in significant losses for many of these investors. In retrospect, it became clear that the dot-com bubble was a result of a perfect storm of overvaluation, unrestrained speculation, and a fundamental lack of understanding of the new digital business model. Let's check some examples from the field of engineering as well. One example is the failures of O-rings in the Space Shuttle Challenger. On January 28, 1986, the Space Shuttle Challenger broke apart 73 seconds into its flight, killing all 7 crew members aboard. The cause of the disaster was the failure of the primary and secondary redundant O-ring seals. Evaluations of the design in the early 1970s and field joint testing showed that the design with the O-ring were not acceptable. However, those concerns were ignored, as the decision makers were very confident of the design. The Tacoma Narrows Bridge was a suspension bridge that opened in Tacoma, Washington in July 1940. It was the third largest suspension bridge in the world at that time. However, it collapsed just 4 months after opening due to aeroelastic flutter. Engineers and designers relied heavily on existing models and understandings of bridge design. However, they did not account the new challenges that they could face when they pushed the limits of what was possible with suspension bridges. The Boeing 737 MAX, a fourth generation Boeing 737, was involved in 2 fatal crashes. Lion Air Flight 610 in October 2018 and Ethiopian Airlines Flight 302 in March 2019, killing all passengers and crew members on board both flights. Investigations into these crashes focused on a flight control software designed to enhance the aircraft's handling characteristics. However, the reliance on this software solution without sufficient broad pilot training on its functionality or extensive testing under a variety of failure scenarios illustrated a potential overconfidence in the aircraft's design and safety measures implemented. The examples we saw are the extreme cases, but the learnings from this can be implemented in our modeling process as well. You should be critical at each stage of the modeling process, validating the model results against data, checking the sensitivity of the model to various parameters, and checking the behavior of the model at extreme conditions. You should update your model as new data emerges and list your assumptions to know the region of validity of the model. This will help you identify scenarios where you are extrapolating your model. Let's try to use this principle as we model the atmospheric carbon dioxide levels. Global carbon dioxide levels are at an all time high. Various reports suggest that the increase in global temperatures is correlated to the global CO2 levels. Through today's model, let's get an understanding of the sources and sinks of carbon dioxide and understand how human activity possibly contributes to the CO2 levels. So, with that, we will use this atmospheric carbon dioxide model to model the emissions to analyze um, to understand like how this emissions affect like what are the sources, what are the sinks, and try to get a general understanding of the model. Just to be clear, I'm not an expert on environmental sciences. So today we will try to get an understanding of what are the causes and try to understand this model better, right? Uh,
Yeah.
we will use the business simulation library that we saw in the previous session and try to use it. So here the plot that we have. Before we start, I just wanted to briefly discuss what this plot shows so that some people who are seeing this plot for the first time, they don't get confused. So here the blue curve represents the atmospheric CO2 levels in parts per million. So when you refer to the atmospheric CO2 level in all the research papers, you would see them as parts per million or sometimes in giga tons and those unit of measures. So here you could see since 1990s we have a upward trend of the emissions, right? And here the gray curve which you could see here, uh, which is measured in CO2 emissions in gigatons, right? So this is in gigatons of CO2, and you could see, and this gray curve represents the contribution from humans or human related activities, right? So this is how
Okay. Then Ankit, the blue line shows
the
the total amount.
yes, the blue line uh, and you can see the axis on the left hand side. It shows the atmospheric CO2 levels, the total atmospheric CO2 levels, whereas the gray curve here shows the contribution because of human related emissions, and that is measured in gigatons and it is expressed on the right hand scale. So if you're trying to understand what this plot is, it's those things.
Yeah. Thank you.
uh, right. So when we started thinking about modeling the CO2 emissions, uh, we did the literature study of what is of how people have actually modeled it and what are the reports. And one thing that we found is there is something called a global carbon dioxide budget. So which is provided by this global carbon project. And this, just to give you what we are seeing here. So here there was analysis done between 2002 and 2011, and here they have identified the different sources and sinks of carbon dioxide, along with what are the yearly emission values from those sources and sinks. So here you could see. Let me zoom it for. Sorry, let me zoom this further. So here you could see the fossil fuel and cement, the release, they are the sources of carbon dioxide, and we have 8.3 gigatons of carbon that is released per year. So with that, this is important. So here the units for this measurements are in gigatons of carbon, right?
Okay, not in ppm, the one you showed,
No.
right? Okay.
So in this type of study, there are three units. One is uh, the ppm of carbon dioxide in the atmosphere, and sometimes people use gigatons of carbon dioxide, or sometimes they use gigatons of carbon. Right. So there are three
Okay.
different things. And in this plot, the values are in gigatons of carbon.
Okay. Okay.
So here you could see you have the fossil fuel at 8.3 gigatons of carbon, and then the next one is land use change. So when the forestry is used for some other purpose, like for farming and all, so there is a land use change, and that releases carbon dioxide to the atmosphere. So those are the two major sources. And the major sinks, or the things that absorb carbon dioxide, is in the land and ocean. And in the land you have the different plants which use carbon dioxide for photosynthesis, and in oceans you have algae and all, who also use carbon dioxide during photosynthesis, right? So
Like
they also absorb.
like planktons, you mean?
Yes, like plankton. Yes. So those are the uh, two major sources, and land sink and ocean sink are the two major sinks of carbon dioxide. And the remaining, the imbalance or the difference between those rates is how much atmosphere, how is the the differential is the amount of carbon dioxide that is remaining in the atmosphere, and and that is leading to the increase in CO2 levels, right? And with that,
Right.
just to be just to also mention here, so when we talk about this carbon cycle and all, so there are two different uh, terms one should be aware of. One is called fast cycle and one is called slow cycle. So slow cycle is basically the rocks and the fossil fuel conversion and other things, which takes like thousands and millions of years, right?
Oh,
So
okay.
you have those long or slow cycles. But to understand the carbon dioxide um, increase in the atmosphere, we use a fast cycle, and these are the major components of the fast cycle, which have an impact in, let's say, in decades, right?
Okay.
So that is the fast cycle, and we will be trying to understand the increase in emissions using uh, that concept, right?
It is more interesting than the slow cycle. At
Yes,
least we can outlive that.
yes. uh, right. And during this modeling process, um, we will try to understand how why it is, why we should stay critical to our model, right? So, and just before we start, I also wanted to make it clear, the objective of this model is not to get the exact quantitative data and compare it with real world data, but the objective of the model is to understand what are the different sources, how the dynamics happens between them, and what are the different types of curve characteristics that we can analyze, right? So we want to see a qualitative trend using this model to get a more
Okay,
quantitative.
then what you are saying is that we will have like a reference,
Mhm.
and we will model whatever we think, a digital twin of the system we are anticipating, and we will match them to
Yes,
see whether they are
we
approaching
will
each
try
other.
to match the trend,
Yeah.
not the exact
Okay.
data, because
Okay.
to match the exact data you also need you need a more detailed model, and
Also, data manipulation maybe. Does it?
yes, and calibration and things, right? Okay. So uh, based on what we have learned so far, Vedat, uh, this sources, sinks, storage of the difference, I think if we hear these words, I think the library that we can use to model this is the business simulation library.
Oh,
On
this is so unexpected.
Yeah, because the business simulation library is based on the system dynamics metaphor, where you have flows, stocks, and it is easy to model those kind of systems using this metaphor, right? So
Yeah.
we will try to use what you have learned so far on last Thursday and Friday, and try to build the model, right? Okay, so this is what we are going to build first. So here you could see we have um, two different type of components. One component which has the label of growth, and another component which has the label of decline, right? And you have those the fossil based emissions and the land use change emissions, which are the sources. They are growth, and then the land and ocean, which are sinks, um, which absorb the things. So those are in decline. This is new because In the last session, when we discussed, we only talked about a given amount of quantity, right? We talked about a population group in which total population was fixed. But in this scenario, what if, how can we model things that we are getting every year, right? Like we need a source,
Right.
infinite source. So what this blocks do is, in the growth block, we get the quantity from an infinite source, and then in the sync block, we we dispose of, or we remove the things to infinite source, right? So that is, so
Mhm.
that's what these two models do. Okay. Okay, with
Okay.
that,
So
let's get
yeah. So what is in the middle? I mean, we can
yes.
somewhat relate
Yes. So this is something
sources
that
and
we
syncs.
saw with that in the last session. So this is stock. So here what will happen is, we will so this is basically the emitted carbon, is the this block represents how much carbon is stored in the atmosphere, right? So we have sources that are going into the atmosphere, and we have this land and ocean, those are sinks, which takes CO2 out of it, right? And of course, if people are coming from different domains, one could notice that we don't have a signal block, which might be confusing for some people, because in Modelica we are the a-causal way of modeling, and um, the way things go in one direction or the other is determined uh, by the
Energy
equations.
levels, how
Yes.
much inputs and output we have. So
Yes, because you could see here that from the emitted carbon we have land and ocean, so there is a mass separation, right? And then we need to account for the mass conservation. Like if the CO2 is going,
right,
so we need to conserve those things. And similarly, when things are coming in, you need to add them together. So those
it
things
is
are
rough. Mhm. In a way that resembles of like we have a water tank in the middle with two openings,
yes,
and we have two water source. We are trying to fill that tank.
yes.
Okay, yeah.
Okay, so with that basic understanding of what this model is, what we're trying to do, let's get started and do our model, right? Okay, so of course we will use system modeler, and I think people who have attended the past sessions, they would have the business simulation library loaded. If someone has not loaded the business simulation library, they can find it in the downloads folder. And then we will be using the modeling principles package to create our model inside this. And here we will start with the uh, critical to model
So
package.
Ankit, before that, you mentioned the business library. So we noticed that some of the audio has the older version of System Modeler. Do they have the latest version of business simulation, or how does that work?
um, right. um, so for this course, I have used the latest version of business simulation library. If someone has an older version of system modeler, they perhaps have a older Modelica library uh, um,
Version?
installed uh,
Okay,
and that might lead to some incompatibility between the two libraries. One way to fix those changes is updating your Modelica library, and in 13.3, if you're talking about the last version,
right,
you can upgrade your Modelica library by right clicking on Modelica, and then uh, version, and then selecting 4.0.0. In the older version, we have Modelica 3.2.3 library. Now one can upgrade to 4.0.0.
right.
So
And they can download the latest version of business simulation
yes,
library.
yes, and
It
that
will be
and,
compatible.
most of the components should be compatible.
Okay.
Right. Okay. Okay. So now let me open the step one uh, uh, model from the exercise package. And to recreate our model, uh, I will we will use the business simulation library. In the last session where we used the business simulation, we made use of stocks and flows. And in this session, we will use this another library, which is named sources and sinks, right? So we will make use of this library. And if I open it, you could see there are different type of components with different type of dynamics in it, right? If you can have a exponential change, or you can have exogenous change where you define the rate manually, or you can have growth or logistic growth. Those kind of uh, uh, different sources and things are possible, right? For the sources, we will use um, the growth component, and let me drag it in, uh, and then I will rename it to, let's say, uh, land use, right? And then I will need another source for the fossil based emission sources. So I will duplicate it by pressing Control D, and then I will press F2 and then rename it to fossil based. Okay, right.
Do you have any reason to use that camel type of naming?
Um, um, so there is no technical reason. One, if I want, I can use the F in capital letter as well. Um, I prefer to use it in smaller letters. The starting is in smaller letters. The reason being, um, when I create a library and when I create a top level component, like basically the model name. So usually I have the
Mhm.
model name that starts with a capital letter. And what happens is when I create a component, I'm creating an instance. This is going into more technical, I
Yeah, yeah,
know,
and so,
but
but here,
usually,
why haven't you used, for instance, the capital F?
yes. So when I use components, I use a, standard naming principle that I name components with a small letter, and I name models with a capital letter.
Okay, can we have any problem when we ship this model to Mathematica? It might be that reason.
No, 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 no.
I mean, like the function names maybe in Mathematica that's all
Uh,
start with capital. Uh,
no, not that I'm aware of.
okay,
No, it
okay,
will not
yeah,
have, because you wrap the model name in a string, so you actually kind of avoid the function names that way. Yeah.
okay.
Okay. So now, since we have the sources in place, I will use a text to give it a nice name, sources, just to distinguish it. And then we will, for the sinks, we will use a decline component, which is, and from the icon, from the, you could see that in the growth,
Yeah, can we zoom in a bit? It is really hard to see. At least we can just focus on the icon. Yeah,
yeah,
here. Yeah,
here, and I will remove this. So here you can see in the icon that you have a cloud, which usually represents an infinite source, and then you have a arrow which shows that when you use this component, you can only have things out from it. You cannot send things into it. So it has those constraints inside built in, right?
okay. Yeah,
So yes. So now we will use this component for sources, and we will use a decline component for the land and ocean sinks. And here, if you see the icon, you see that you have a cloud, which is the infinite reservoir, and then you can you can only send in uh, content inside. You cannot take things out from this using this component.
right.
Okay.
There is no limit in that reservoir that you are
Yes.
saying, right?
So those
Yeah.
reservoirs are infinite sources and infinite sinks. Okay, and then let me uh, s- uh, change the shape. Let me flip it, and to flip it, I will use my flip horizontal icon here, and you see it has been flipped. Let us rename it to land, and then let's duplicate this, create a copy, and rename it to ocean. Right, and uh, to represent the atmosphere, we will have the uh, a stock, and we will use a material stock because material stock avoids has a constraint that allow that prevents the value to go below zero. So it has those equations built inside it. So I tend to prefer use the material stock, and then let's drag it in here, and I will say uh, uh, emitted CO
Atmosphere growth.
atmosphere CO2, right?
Right.
Okay, so yeah, so now we
So this
have,
is not the growth. This is what we have, right?
so this is basically the tank where we will send in carbon dioxide from fossil based and land use, and we will extract um, carbon dioxide by land and ocean sinks.
Right.
Okay, so now let's connect the fossil based with the atmospheric CO2 and the land use with the atmospheric CO2. And similarly, let's connect the land and then the ocean, right? Okay, so let me give a couple of minutes of people to model this. Okay, Vedant, do you have, is there, are there any questions to this point?
Um, so maybe you can explain how could you draw those connection lines in that way?
Um, oh, so you mean this?
Yeah.
You mean this? Okay, okay. So the thing is, I, I like the my models to look neat and sharp, and so when you create a connection line, let's say I start uh, drawing in, and then let's say I want a edge at this point.
Okay.
So I would just
One
simply
for yeah.
click on that point, and when I click that on this on any on the point in the canvas, it becomes one of the nodes, or it should become one of
Okay.
the nodes. And then and when I click on the other point, it becomes another node, and then
Uh,
uh, I can connect it.
Yeah, it doesn't allow us now. Is there
No,
any other
no, it
styling?
doesn't allow us because you see we have already connected the atmospheric CO2 with the ocean mass port. So we are trying to have a double connection. What does that mean?
Right.
Between two different between the same components, right? So that's why the tool was able to figure that out and give us that. Let me rename my text to sync. Okay, fine. Okay, Vedat. So now, since we have the model ready, let's get back to the presentation and try to see the data for the different um, sources and sinks, and try to populate
Right.
our model with that parameter value. Okay, so let me get back to our model. So let's start with the fossil fuel based source. So here you could see we have 8.3 gigatons of carbon per year. So here we have a rate of uh, of carbon that is going in to the atmosphere, and that is 8.3 gigatons of carbon per year. So let's try to um, populate it. So I will select the fossil based source, and then we will start with a constant rate. Let's say we have a constant, the value that we got, let's assume that it is constant, right? So we have
Right.
has constant rate goes to true, and then the output type, for this source is a rate that we want to to have. It can have different other types of output types like monetary flow, and other volumetric flow and other things which are relevant when we model uh, some other domains. But for now, just let's use the dimensional rate of flow 1 per second, uh, and then we want the value, the display unit in per year. So I will click on the unit 1 per second, and then I will change the display unit to 1 per year calendar that we have
Okay,
here,
okay. So we
right?
just change display unit, whatever we register there, set there, we will use in
Yes.
that.
So
Yeah,
under the hood, what will happen is, what value we give, system model will convert into the base unit, because all the other model equations, they use the base unit to work, right? Okay. And I
right,
click OK. And then here, when I specify 8.9, you could see that my value here is 1 by y, uh,
right,
is in
right.
per year, right?
So
Okay.
now, so we had that structural parameters there. You
Mhm,
make that true. So
mhm.
when it was false, how was how did it
Okay.
look like?
When I had false, uh, you could see that when that is false, it means that my real input connector was activated. So I can define an input to my block that defines the rate,
Okay,
right?
okay,
In this case, I will start simple. So I'm just interested with a constant value. So here, that's why I have this has constant rate goes to true, and then I set it to 8.9.
right. We have a question why it is 8.9 but not 8.3.
Uh,
Did we
yeah.
misread?
Oh,
Oh,
sorry,
yeah,
sorry.
yeah,
It,
yeah, yeah.
it was
Thanks, Randy.
an oversight.
Yeah,
Sorry. So 8.3. Yes. Okay. For the land use, it is 1. So let's take this as 1. So with the same process, I will select my output type as per second, change the display unit to 1 per year calendar, click OK, and then has constant rate set to true, and then let me put it 1 year calendar. So you see you have 1 by y here.
right.
Okay. Okay. So here we have 8.3, we had 1, and similarly we will fill in the values for land and ocean. So let me first, you saw that the output type and has constant rate I had to change for all my components. So rather than doing it individually, let me select both of them by selecting them using this uh, by creating this selection box around them. So both are selected, and since both the elements are similar, I can at one place provide the value for both of them, so I don't have to do it
Okay.
multiple times.
So it should be, this case is valid for the similar components, or if any components have the same parameters.
um,
Let's have a look.
if any components have the same parameter.
Okay, okay,
um, so yes. Okay, so for instance, if let's say if we select both of them and I press shift and I select the sync as well, so you see that the output type was same. uh,
right, right. We can
so
set all of them at once.
only the things that are common among everything. uh,
Okay,
but it gets a bit tricky, because one might observe that rate and constant rate are present here, but uh, rate and constant rate are also present here, so why were those not selected? One might have those questions as well. But then there are the it it depends how the component was constructed. Sometimes you extend, like you use inheritance to create a component,
oh
and
right,
that's why it misses those things. But if you use normal components, it tries its best to figure out which parameters are common among all of them, and then you can set them at once. Okay, so now that we have selected land and ocean, let's select the output type to 1 per second, uh, and change has constant rate to true. And if I go back to my notebook, So you could see the land sink contributes to 2.6 gigatons of carbon per year, and the ocean sink contributes to 2.5. Let's update those values. So land is 2.6 uh, per year. For some reason, my display, maybe I didn't change it. So let me change my display unit for those as well.
Right.
Okay, I
That's the
have it
issue. Yeah.
2.6, and this one, and for the ocean, I will change my display unit to 1 by year calendar, and then it is 2.5, right? 2.5, 2.6, 8.3, uh, 1.
Well, yeah.
Okay. Um,
What
um,
about atmosphere?
right. So, um, right. Um, right. So there are two ways of, let's start by, let's assume that, let's start by uh, um, considering zero. So let's say that we are starting at a particular time, and whatever value it is, it's zero. So let's check uh, if we are accumulating the difference, right? And in the next stage, we will add the initial value, because first let's test up to this point it is working, because then will introduce another concept, another conversion, and it might become too complicated. So let's break it down,
Okay.
right?
Okay. Yeah.
Okay. Okay. So before we simulate it, let's set the experiment setup. Uh, okay. So let's say that, let's take a time unit of year, and if I go back to my model, it says from 2002 to 2011. So let's start with 2002, right? And let's take a start time of 2002, 2003. Let's first simulate it for 1 year and try to see the response.
Right. Yeah.
Yeah, click OK. And then let's simulate by pressing the simulate button. Let's see. Okay, Vedat, are there any questions up to this point that I can take?
Uh, no, I guess so far so good.
Okay, for some, yeah, okay.
So now we run the simulation.
Yes. So now once we have the simulation up, like the simulation is done, I can plot um, my atm- uh, the value of the atmospheric CO2, and you could see that at the start we start with our initial value. In this case, we took the reference as 0, and then in 1 year we have accumulated around 4.19 uh, gigatons of carbon, right? So this
Okay.
is a linear trend. And if I go back to my model, so here it says 4.3. um, for some reason the values here do not add up, but it's 4.1 if you do the maths, uh,
Right. Right.
right?
And there are some deviations. Maybe it's because of that.
Yeah, maybe some, yeah, right. So far we could see that, okay, we had the model, and this is the trend that we would expect, right? uh, just because we had the fossil fuel 8.3 and zero point 0.9, and uh, the emissions is 2.6 and 2.5. Okay, so right, up to, I think up to this point of simulating this value, and to get this plot variable, I went inside the atmospheric CO2 component, and I plotted the value of y here, right?
Okay. So why can't we see the unit of the
um, uh,
atmosphere?
yes, so the reason is I did not set any values in my stock. So here in my output type I did not set anything. uh, so one way of setting a value is amount, which is each, um, uh, and I can set it as an amount, and then if I simulate this, so you will see a term called each. So unit of one, we refer to it as each in this library.
Okay. Okay.
right? And then it
So
is
other
represented by the.
than that, when we look at the land use, right,
Mhm,
even if we register one,
mhm.
it doesn't look like one. It is
Yes,
like 0,999 something.
yes, it is because of the some conversions that when with the display unit and the base unit. Because of those conversions, sometimes there are some, because we use real numbers for this, there are some issues, not issues, but uh, there are some
What happens if we write one
transitions,
now?
right? If I
Oh, okay,
Yes, so it does those conversions, and then we have this issue here, right?
okay. I guess Sergio will answer that.
Yes.
He is the guy
uh,
behind the scenes taking care of these details.
right. And okay, okay, with that, so let's get back to our model. Let's get back here, and let's start from here. So now, um, so far we have modeled the rates. We have modeled a reservoir to store them. Okay. Now, as I said, the value of atmospheric CO2, the plot that we started with this, we started talking about ppms, and then the value that we are getting now in
Unitless?
is zero. The starting is zero. It does not relate,
Yeah,
right,
yeah,
to the data that we saw, right? So let's use the proper values. For 2002, if I go back to our presentation, and if we see our, for some reason it's scaled. Okay, if you see our uh, plots here, so you could see for 2000, um, we have around 360 ppm, right?
right.
So for 2000, as you can see here, we have something around 360 to 370 ppm. So let's say 370 ppm, right?
Yeah,
So for the atmospheric CO2, the initial value is 360 ppm, but that is in ppm, and we are talking about talking in terms of gigatons of carbon, right?
right, right. So we need to do some conversion for that.
Yes. So, and this is something that one can search in the Google. But when you convert 1 ppm of CO2 to 1 gigatons of carbon
Gigaton?
dioxide, you have a scaling factor of 2.13. So
Okay.
once 1 ppm of CO2 is equivalent to 2.13 uh, gigatons of carbon, right? And that you do using the molecular weight, and from those relations, one can compute
Yeah,
those
we
things.
trust you, Ankit. Whatever you say.
Okay, right. So now, with that, we have an initial value 360 times 2.13, which is in gigatons, and then we have this values. But as I said, the values that we uh, okay, let's simulate this first, right? Okay. So now with this initial value, let's simulate this and let's see what we get. Right. So now now we start from, uh, if I plot my value at, if I take a measurement at the initial point by doing control plus left click, I can see the value as 766.8 gigatons of carbon
Right.
of
Yeah, we
carbon.
have a question from Francisco. He
Mhm.
says that ppm is concentration, but gigaton is a total amount. I guess this is
Um,
the ratio. I mean, if we consider whole atmosphere, right?
yes, it is ppm, in terms of in terms of volume. It's called ppmv actually. Um, uh, I actually don't know more, because whatever I say, I will be trying to
Okay.
extrapolating my knowledge.
Okay.
But
Yeah.
this is what I don't want to extrapolate. I just want to say that I don't know. This is what I got when I looked into the literature. For
Okay.
example, let me see if I have those things here. No, I don't have it here. But one
Yeah,
can do
yeah,
a, one can do a search, and then one could uh, see how those conversions are done. I am not an expert on that. Okay, so now Vedat, we are seeing the value in gigatons of carbon, right? But we had values in ppm, and it would be nice to stick to one unit than switching between various units, right? So it would be nice if you can see those values in ppm as well, so that we can relate to the data. So in order to do that, let's go back to model center. So here, when you look at a stock, you have this real output, you have this green triangles, right? So this
right,
triangle, they actually give the current value of the stock, right? So these are the output from this stock, and at any given time instant, this output values tells us how much quantity is present inside the stock. So it gives us the current value of it, right? And let's say if you are interested to see the results in CO2, we would use this result and do some conversions, and then try to plot the values in CO2, right?
right.
Okay. So for that,
So
mhm,
those outputs, what type of outputs, Ankit, those?
those outputs are the real values, real
Okay,
output with that. So
in which
when I
we
mean
can assign any type of units we like.
yes, any type of unit that we like, under the hood they get converted to base unit,
Okay,
and that's how it works. And the thing is, when I say real, that also means that you can integrate or you can connect the out. Let's say you want to use the output of a stock in some other equations, right? So you would
right,
connect this block to other mathematical blocks, and then you can compute something out of it. For example, in this case, I want to get the value in ppm, right? So I will do a conversion for that. To do this, if I go to the business simulation library, I have uh, converters in it, and inside converters, I have a gain block, right? So which will just multiply a value to the output thing, right?
right.
Um, so let's
So
drag the.
Ankit, do you
Mhm.
know exactly where this component is? Is there any other way sometimes find this component instead of? I mean,
Yeah.
sometimes it might happen, right? I mean, you might know some exact component, but you don't know where it was located.
Yes, yes, that happens. That happens, and that happens very often. For this demo, actually, I know where the component is, so I'm trying to go there. But usually, what happens is, let's say, I know what block I'm looking for. For example, I need a gain block, right? So I know the
Right.
name of the component. So here you could see in the class browser. I cannot zoom this further, but here on the top
Yeah.
left, you could see this filter here. So here you can write, for instance, gain, right? When you type in gain, all the different blocks with the name are displayed. And you could see
Oh,
I have the gain block here as well. So I can drag it in directly from here as well. That's fine. And that's
yeah, that's great.
when you start modeling, you actually know the different names. For instance, if you want to sum something, you just search for sum or total or product, rather than browsing through all the sub packages. That's
It
more
is all you
faster.
are saying it is also a good practice to check. I mean, you might a block component in your name. I mean, even if you haven't seen that, like sum, like integral, you
Yes,
can
yes,
just search for it whether it exists.
yes.
Yeah,
You can do that. So with that, now I have a gain block. Let me give it a suitable name by clicking F2. Uh, let's say uh, CO2 in, okay, uh, atmospheric CO2 ppm. I'll give it a name. And since I told you before, we have a conversion factor of 2.13 to get back the value in ppm. I will just have 1 divided by 2.13, right?
right.
So that's the conversion I have here. I will zoom back to my model and let's simulate this again. Right. Okay, so now I will create a new subplot by clicking on this on the new subplot icon here, and then we have I will just close this atmospheric CO2 in ppm, and I will plot this. So now you see the value in 360 ppm, and it goes to 362 ppm, right?
Okay.
So now at least we have the output in a dimension that we can actually compare it with something else.
Right.
So
Right.
that's why it becomes easy to validate model. So when you create a model, if you want to validate with data, it's nice to convert it in a form that is comparable, right?
Right.
Okay,
So what you
so
are saying that we are happy with this model, or
let I don't know. Let's see what would happen
shouldn't we stay
2023.
critical to our model?
Yeah, you see, so our model tells us that in okay, let me delete my subplots, my measurements. Okay, so my model tells me that in 2023 we have a ppm of 401 based on this simplistic model, right?
Right.
And if I do a Google search, or not, yeah, I will not do a Google search. I will use Wolfram Alpha. Oh no,
Okay.
I can just use this plot that we already have, just to
Yeah. Right.
not spend that
Right.
much time. So here we could see in 2023 we have a value of around 410, I would say, or 12 ppm, right?
Right.
So with that we have a model, and the value is, of course, we said it's a qualitative model, so we are getting somewhere there. So are we happy with it? Is this how it looks in reality? Is it like a linear curve? What do you think?
It is mismatching. I guess we have the fidelity issues here. So,
Yes. Uh, right. Let's look at some real world observation data. Like we have
and
different.
also, I mean, when we look at this, it looks like always it is increasing at steady pace, right? I mean,
Yes.
there is no any.
There is no growth.
Yeah,
Things are constant. Like we have reached a saturation stage. We have got a constant growth
right.
in
For instance, we
emissions.
have so many, like, I don't know, like plants we have, they shed their leaves and etc. Doesn't such thing affect this
I don't
figure?
know. Let's look at, so once we have a simplistic model, let's go out and find out how the actual data looks like.
Oh,
So the data that we saw was an average data for a year, and then how the average. Uh, so this plot is basically an average plot across through the years, right? So if we
okay,
look
yeah,
into more detail, like, like how does, like in a year, is it always increasing, or does it go down, go up? How does it look like? How are the variations within a year? And
right,
then if we look at this CO2 reading, and this is from the Mauna Loa Observatory. So there are so this observatory has been keeping track of the CO2 emissions since 1959, right? So and a lot of the CO2 emissions data are from this observatory. And here if we see in 2015, you could see that there is a trend uh, in the CO2 levels. Like in May, uh, when the summer starts, at least in the northern hemisphere, you have a 400 ppm, and then uh, as we go towards winter, we have a fall in CO2, and then as the winter arrives, the CO2 level goes up.
right.
What might be triggering this?
Yeah, I will still say the same. I mean, because of, I guess, falling leaves.
Yes, I did a quick like once I had the model, I checked the data, and I saw that there is something that I don't understand. I checked into the literature and tried to find why this happens, And one of the reason that this happens is because in the northern hemisphere we have a very huge landmass, right? So the amount of let's see the model first. So we have a land and ocean as a sink, right? And in winter, what happens? Okay, let me get started. Okay, since we have a very big landmass in the northern hemisphere, whatever happens, the changes that happens in the northern hemisphere is reflected in the CO2 levels, because as we have more landmass, we have more plants uh, in the northern hemisphere, so they can absorb more carbon dioxide. So whatever happens with the plants in the northern hemisphere, they have an impact on the atmospheric CO2 levels, right?
Okay.
And
Yeah.
what happens in winter is you have uh, you, the plants go to a dormant stage, right? And then you have a lot of leaves, uh, uh, leaves that fall, and when they degrade, they release CO2 levels. And since you have less sunlight, the photosynthesis activities are also lowered.
Oh, they decay, and that's why also that increase. You say.
Yes, yes.
Okay. Yeah.
And as the winter
Instead of
progresses,
being sinks, they become source as well.
yes. So in winter,
Okay.
uh, they become dormant. Photosynthesis activities uh, slows down significantly, and they start emitting more, and they don't act as a sink.
Okay.
And similar pattern can also be observed when you think about the algae in the ocean as well. So
Right.
some kind of behavior is also reflected there. However, I'm not so sure about the algae part. I have to do more research. But for the land part, from the research from the data that I saw, it's because of that. So
Okay.
and then you could see that in the summer, uh, like from May, as the photosynthesis activities grows, or the plants start absorbing more CO2, and you could see that they start taking in more CO2 from the atmosphere. So that is one of the findings, uh, like from the literature that I could find, and that is what explains this behavior, right?
Okay. So, what are you planning to do? Cover this dynamics?
Yeah, I don't know. Let's see. So if we get back to our model, or we have a model, I have the model here itself, so we can look at it here. So we had a constant rate for land and ocean. Perhaps what we could do is add a seasonal variation. And let's get start simple by adding a sine curve that reflects, right, the transition that happens through the year, right?
Right. That is. Yeah. It looks in a way
Let's
sine wave. Right? Yeah.
Yes, let's start simple and just try to use that instead. Okay, let's get back to our model. I will double click to zoom back. Um right. Let me use the
Oh,
class.
yeah, yeah. John is asking whether you can show how to save this step one model.
Um,
S-
right. So to
when we are
okay, so you see with that here, if like if you can see my model principles package, you see that the step one is bold, right? So
right,
this means that I have made some changes to my model, right?
which
And
is not
that's
saved.
which is not saved.
Okay,
So I made some changes which is not saved. That's why you have it in bold, right? And
yeah.
let's say you want to save the model at this stage. So I will right click and then save. And then
Just
if I do
right,
this,
just that model,
yes,
right?
this saves the entire package actually. So this saves then, because when you save the model, you have to save the containing packages as well.
Okay, assume that we made changes both on step one and step two, and I just want to save on step one. Is that doable?
Uh, uh, Not, no.
Okay.
It will save the model. This model, there are advanced concept like can save. Imagine that you're working on a big project, right, where there are
Right.
multiple people working on different sub packages. Then it's
Right.
an advanced concept, so I'm not assuming all people should understand this, but just for the curious people, how it works. So let's say you have a very big modeling project, like when we do projects, someone is working on one package and someone else is working on some other package, right? So we
Right.
save it as a directory structure, and when we save it as a directory structure, then it is possible. But the modeling principles that I have sent you is a single file with a .mo extension, so it's not in a directory structure. And in that case, when you save it, you are saving the entire thing,
Okay.
right?
Okay.
It's a bit advanced, so I will leave it at that. But for now, uh, if you do multiple changes and if you save it, the entire thing gets saved. Or one other thing is, rather than right clicking and saving, you can click anywhere on the model canvas and then just press Control S, and that would save as well, right? So you
Yeah.
can
Thank
just
you.
press
Thank
anywhere
you.
here and then do Control S. Okay. Okay.
So
Let's.
also let's assume that we created this step one, right?
Mhm,
And instead of creating all the components, all the dragging and finding and renaming
mhm.
uh, things we did here, we just want to use this step one as a starting point for the
Okay.
step two model.
Okay. Okay. So let's do that then. Let me just delete step 2 and step 3. So let's say we want to move to step 2 and we want to save our work up to step 1 up to step 1. So let's do control. You can right click and then there is an option called duplicate, right? And when I duplicate this, you see I'm asked that it will create a new copy, and it will create a copy inside my exercise folder here. And then I can click
Okay.
OK. And here you could see my step 2 is created with which duplicates my step 1. And now I can keep working on step 2, and my step 1 I have saved the state, right? So I've created
Right.
the model. Okay, Vedat, let's implement the seasonal variation for now, right?
Right.
uh, so I will go into the converters package inside the business simulation library, and I will look for a component. uh, and as you can see, this library has converters, so it basically takes an input, does a transformation, and gives an output, right? So that's why it's a converter. What I am actually looking for is a source, like a sine input. That I'm looking for is a source. It gives me a sinusoidal source, right? So I go into the information sources, and then I could find the sine input inside the sources block, right?
Right.
Let's drag it in here, and let us flip this by using the flip icon on top, and let's rename this to seasonal variation. Okay, and let's click OK. Right. So now once we
And
have.
Ankit, we are also 1 hour in. I guess we can roughly say we have like 15 minutes to 20 minutes left
Mhm.
to wrap up. What do you say? So if people want to stick around,
Yes, so
y-
um, so for people, if you have they have something else planned, they will of course get the recording and then they can watch the content. So we can like extend for 15-20
mhm,
minutes. So it's
right.
perfectly fine if someone has some other work to go, and they will have the recordings later on,
Yeah,
right?
yeah.
Okay. So now with that, once we have the seasonal variation, uh, let's let's go ahead and select the output type of my seasonal variation. And here we know that this output type is a rate, right? Like what will happen during the year, how the rate changes during the year. So I will select a output of 1 per second, and if I scroll down, I have this dimensional rate flow, which is in per second. I select that,
Okay, yeah.
and you see that when I selected this, um, all my other components, they got some units in per second. thing, right? Okay,
Right.
so uh, let's start simple with zero offset, zero start time, with an amplitude of, let's say, 2.6. um, and then, no, let me just change the display unit to 1 per year calendar that we have been doing for all our components,
Right.
and click OK.
Just
And
to be
then,
consistent.
and 2.6, let me just use the value 2.6. And the period, with that we want the fluctuation
Of a year or half a year. I don't know.
of a year, let's say.
Okay.
Let's start
So
with
in the
1.
model, we saw just one down, right? I mean, in
Yes,
between two, right, two summits.
yes, you could
Yeah,
see, um, from May to May onwards you have one pattern, one
yeah, yeah.
kind of one curve,
One cycle.
one cycle. Yes. So now, we set a value of 2.6 to it, a period of 1 year. Phase is basically how we want to move the sine wave across time, and that is something we can always set once we simulate the model and when we see the
Right.
results, right? Okay, with that, now we have the seasonal variation. Uh, let's assume, I'm making an assumption here. Let's assume that this seasonal variation is for the land and the algae growth in the ocean as well. So for both of them. So let's select both the components and then check change has constant rate to false, right?
Okay.
And when I do that, you could see that I have the inputs on for both the
Right.
cases,
Right.
right?
But Angel,
And
we had some parameters, right? We set. What happened those?
so when I set this
So
has
we
constant
can
rate
still
to
see
false,
those, right?
so when I set this has constant rate to false, the rate is disabled so that you're not confused uh, if this is enabled, and you don't try to override it. So when you
Okay. It
set,
it will be overruled, you say.
it will not be used.
Okay. Yeah.
It will be
Whatever we
it
gave
will be
them.
overwritten. It will be
Yeah.
overwritten. So the data is saved so that next time if you want to change it, you don't lose the data, but this will not be used, right?
Okay. Yeah.
Okay. And then let's try to connect our seasonal variation with this inputs, uh, and let's try to let's simulate now. Right. Okay. So I will create a new plot, and then I will plot our atmospheric CO2 here, settings. So 1 year, right? So with that, we did not get exactly what we saw, right?
Right.
So here we have
Oscillations are
360.
quite narrow,
Oscillations
right?
are quite narrow. What might be happening here, right? Let's try to troubleshoot this. Why this is happening? Um, let's say, let's plot the um, let's go back to our model. Let's plot how the rate of the land is working, right?
Right.
Let's try to see if that corresponds to what we were trying to do.
Right.
So if I go for land and then I have the rate information here, um, you
Oh,
could
can we
see
make
that.
the as a year? It is.
Yes, yes. Okay, so to change, let's say we have plotted a variable and I want to change the display unit of my y-axis. To change the display unit, I can right click on the y-axis, go to display unit and change it to 1 per year. And here you could see a curve like this, right? And then if I create a new subplot and I plot my seasonal variation from it, you see that
Right.
you see that what I wanted to do was I wanted to have a dynamics where my sink tries to give CO2 back uh,
Right.
during a particular time period, right? But what
Right.
happened was those dynamics were lost, and and I have only it was only allowed to get in, but it was not allowed to go out,
Right.
right? And that is understandable if you think about it. It's because we started with saying that we have a decline, something goes to the infinite source, but something cannot come out of it, right?
Right. Right.
But
By default, we assume that it will be always sync.
yes, so
But
even if you
now
give
we
a
are expecting it to show some source then.
yes,
Right.
and and that's why we are not getting that behavior here, right? But
Hopefully,
what
we
if
have another component for that.
yeah, because in some cases maybe we are trying to play around different scenarios here, right? Maybe this is not the case, but we are trying to see if we have how can we model such process where we can have something it goes in, something can go out, right? Something that can
Right.
allow both type of interactions, right? Let's try to see if there is a component and try to test how our model would behave in such cases. To do that, of course, we will go to the flows or we'll go to the sources and sinks. And here we use the decline and the growth component. But you could also see we have a exogenous change or exponential change, both with an arrow. If I try to zoom in here, both with an
Right.
arrow that goes in and goes out, right? But we are not modeling an exponential change in this case. So let's just use the exogenous change instead, right?
Right.
So let me uh, delete both the components and drag in the exogenous change components and duplicate it. I will change the name to land and change this to ocean. Right. And then click C to connect. Uh, okay, let me just flip it. I flip it by using this icon here.
Right.
And then let's connect the atmospheric CO2 to land. Let's connect the atmospheric CO2 to ocean. And if I select both the components, um, I can have an output type of per
Right.
second because that's what we are interested in. Then
Right.
we have it set to rate, and so here by the name suggests exogenous means it's dependent on some external uh, value. So here we don't have a constant rate. Here the rate is defined by external values because the rate is supposed to change as the simulation runs, right? It can be positive or negative depending on which direction of flow we need. Let's connect
Yep.
it to our seasonal variation here and variation here. The ocean is connected to seasonal variation and the seasonal variation is connected to the land. Let's simulate this again. Right. So you could see we have a trend that both the trend are varying, right? But we don't see the behavior as we expect.
Right.
Perhaps our parameters for the seasonal variation are not properly tuned, right? Because the value of 2.6 was an average value, which takes into consideration how much CO2 was given out, how much CO2 was consumed, and that was an average value. Perhaps that value was not sufficient enough for this model.
Right. And it was also for 2 years. We are looking for a 1 year. That might also affect our
Yes,
comparing the pathways.
perhaps. Let's try to play around it using a panel and model. I'll create a panel and let's name it as model parameters. I will add a control object and then for the seasonal variation, amplitude, and then let's play around with the slider. Let's start with 2.6 per year to something like let's take uh, 12 or 15 just to have a extreme value
Right,
and try to see in extreme cases how it works, and then click OK. And now as I change my parameter values, you could see the trend coming in. And perhaps, as you
right,
rightly said, I need to simulate it for a longer time. Let's say 207, for instance, or 2007. And then let's simulate it to observe this characteristics better. And you could see that now when I'm trying to play around with this amplitude, I could see those fluctuations in
right.
the model as well.
Yeah, it looks like more of what we have checked, right?
Yes, it looks similar. So we could model those kind of dynamics inside our model, right?
Right.
Okay, Vedat, are there any questions up to this point?
I don't know. I guess you were really good at. Okay. How can I get show the parameters and units of the newly added blocks and the sign block? Sign block. Yeah, we had the seasonal variation over there. Can
Mhm.
we just check how we added the units to that? So
Okay,
how
so I
where?
selected my seasonal
Yeah.
variation. I selected my rate to dimensional rate flow in per second. So this one I selected to 1 per second. And then to change the unit, I clicked on 1 divided by y here. And then here in the display unit, I could select any unit I want depending on my model. In this
Right.
particular case, we are interested in 1 per year calendar, right? So that's why I selected here. For some other model, maybe I need a different unit, and then I can select the other relevant ones, right? Okay, Vedat. Yesterday you were asking me if we can use time series for some of our components, and how can we
Right.
add time
Right.
series, right?
Yeah. For instance, here we call that thing as input, right?
Yes. So what happened in this model? We have considered uh, the emission from fossil based or from humans as constant, right? But as we saw in the graph, we had a linear upwards trend. So it's not a
Right.
constant, but we have an increasing trend, right?
Right. It
Let's
was
try to.
sharper than sinusoidal, right?
Yes. So let us go back to our model and try to see that. So here you could see since 1900 uh, we have a upwards growth um, for this uh, emissions from
Right.
fossil based sources, right? Let's try to use this experimental data and try to feed uh, to the rate to the rate of our block. So that way we would learn how to integrate those type of data
R-
to our model, and we are not just limited to using the rate or the mathematical expressions like sine or
Right.
other things, right? To do that, uh, we would go to the sources, because of course it is a source that we are trying to use, and then we will use exogenous data, right?
Right.
So as the name suggests here, we can use it as a table that we can supply as an input. And let's try to give it a name, uh, saying human contribution or something like that, right? Okay, so once I have this data, um, let's select the output type
Unit. Which.
of 1 per second. So that's the output type of my block, right? And then table on file goes to false. And now I have to
Which.
specify.
Okay. So it is. If we like, we can just find the file, corresponding file, and use that.
Yes, as we discussed yesterday, it's a bit
Yeah.
tricky because it has to be in a particular format.
Okay.
I typically do it using create data system model function in the Wolfram language, because that way I can use different other types of file formats as well. Uh, uh, so, but you can do that if you provide it in
Right.
ASCII data
So
format.
this one and the component we look at yesterday are
Are
fundamentally
similar.
same. Yeah.
fundamentally the same.
Yeah.
The same.
Okay.
So now let's select uh, table on file goes to false. So you could see my table um, parameter uh, is it's allowed to edit it, right? And if I click on the edit mark here and I go to the edit button, I press edit button, I get to this array editor. And in this
Right.
array editor, so I can define the time on the first column and the value in the second column. And this value is typically in the base unit, like in per second or those things, right? So I can use this table to define my uh, the time series data, right? So let's
Right.
say for 2010, um, let's assume that we have a value of 5, and 2023, let's say this emission will go from 5 to, let's say, 12 or something, so, or so a certain value, right? So we define the years, and then we try to use a linear curve for now, right?
Okay. Yeah.
And then once we define this, we click OK. Now we need to define the time scale, because how you might be interested in values which change per month, per hour, right? You have to tell those things to the data timetable so that we can know like how to interpret those. And then I will change the time scale to 1 year, uh, and change the display unit so that uh, it's displayed properly. And here you could see the time scale is in 1 year. So that means that, so by time scale, what I mean is the values in the first column are based on years.
Right.
So that's what I am trying to mean by the time scale, right?
Yeah. Otherwise, yeah, it will be really hard to. If yeah, this is really nice trick.
Yes.
If yeah, we didn't pay attention to this, it will be really hard to figure out why
Yeah.
we are not seeing what we expect.
Because sometimes you imagine you have hourly data, right?
Right.
Sometimes you might have data per week. So how would one know like what conversions to apply? So as
Right.
a modeler, you need to specify that thing. You need to specify um, the time scale. But when we use this exogenous data, one more thing that we need to also specify is the output type. So here, when I define my value in terms of years and data, we assume that this data is in base units. So that's an
Base unit in the
assumption.
sense that.
Base unit in the sense, if I have a rate, it will be in per second,
Okay.
right?
Okay.
So I need to convert those per second value to per year.
Right.
And
We
for
need
that,
to change the quantity. Yeah.
yes, because we need to change, we need, because that output can be in any unit you can imagine, right?
Right.
It is up to the user to uh, to define those units. And then we have the rate conversion element, which converts those rates to the one that we need. Else you would have to define your own gain block to do those conversions. And just I wanted to make it clear, this rate conversion and is only needed when you are trying to use the exogenous component. When we use a seasonal variation, we didn't need to do any of those things. Those things were
Right.
automatically taken care for us. It's only in this special case where we are trying to use this exogenous data that we have to consider using those rate conversions and all. For other cases, we don't need to do that.
Okay. Yeah.
And
Great.
here we specify that our initial time, like the time in the input, is in years, and the output is in base unit. So I will keep the seconds as default. So what we have here is per year, and we got what we get back is in per second in the base unit. So
Right.
to do that, let's set our fossil fuel based rate to false. So now I have a connector that comes in here, and let's connect it to our fossil based model. So now we have attached exogenous data uh, to our component as well.
Uh, Ankit,
Mhm.
can we go and click edit table and check why we cannot save it? So at which cases we end up being not able to save this.
So let's
So
say,
sometimes it doesn't allow us to click OK.
okay, so there are some cases. For example, let's say you manually created a backspace here, right? So
Okay,
now you could see that my format is not right. So I need to have it in the proper syntax. So then I will put in a curly braces, and then you could see that this OK button is active now. Now it's OK. So what happens? So one way of fixing this. Okay, now I had a dot. Sorry.
right,
So one way of fixing this is just remove the data and then try to update it again. It only happens if you try to manually play around with those values here, because that
right.
takes away those details, right? And now let's simulate the model, and you could see that we have a increasing trend. uh, I don't know what we would get but at least we have data here. So yeah,
Oh,
so now if I let me delete my subplot, and then let me clear the subplot and then plot uh, for the fossil based component. Let me plot the y rate, uh, right? And you can see we have this increasing, the rate is increasing, uh,
it
right?
is not constant.
It's not constant. It has a, because we provided only two values, so it is taking a linear uh, interpolation across that. Okay, with that, so I think we covered what we said we would cover. And as and this is how, and then if you plot it for a longer time, this is how the you would have the contribution of the fossil based, which is growing linearly. You have a seasonal variation, because of this we have the fluctuation. So next time when you see a atmospheric CO2 level chart, you kind of understand what are the different dynamics. And then you could also play around with the different rates and try to see what would happen. Let's say if the plant mass goes down, or if the plant mass goes up, or if the emission goes is stable at a particular value, how would things work? And then you can play around with different scenarios.
Right, Ankit. Yeah, thank you, Ankit. So yeah, maybe
Yes,
it will be
let's,
really nice if you sum
yeah,
up what we have done today.
yes. So basically, uh, just to summarize about this principle that we try to implement and understand the atmospheric CO2 variations, is like we started by defining the model objective, and the objective was to understand how the trend behaves, what are the different dynamics involved in those yearly CO2 levels. We listed our assumptions. We said that we are focused only on the fast carbon cycle, and we are only considering those four sources. There might be other sources which we are neglecting, right? So we list our assumptions and define the scope, and at every step we are trying to see the results, try to compare it with the data, and then try to move ahead. In this case, we wanted to have a qualitative nature of discussion, so we were looking only at the trends. But as you do more advanced models, or more uh, uh, as you do more models, you would uh, actually calibrate and validate with the data, and then you'd proceed ahead.
Right. I mean, on the other hand, when we start modeling this, I mean, we didn't know much about it, right? I mean, what you did most of the time, you just model a thing and just stay critical to your model, right?
Yes,
And try to match what you are missing and etc. So,
yes,
uh, I mean, maybe that is also fundamental and really useful approach while modeling
right.
such. Yeah.
There is a connection by Shumi. She's asking, could you show how to connect dots again? So let's say if you have clicked on one of the the components, one of the connectors, like the connector here, you could see this as a sticky thing, right? When you move your mouse, it just moves, and then you can connect it if you have a compatible connector, right? I cannot connect my fossil fuel output to a real connector, because I will not be able to derive the equations that are involved, right? So I can only connect it to compatible connectors. So here you could see we have the atmospheric CO2, and you have uh, this purple connector here, and when you click here you could connect it. But here now I will get an error because I have already connected it, right? And if you want to get out of this state, like you are in a weird state where you cannot connect, you can just press escape, and then you will come out of that mode. And if you want to select something and you are in the connection line mode, you can select on this arrow button here, so it will bring back to the select mode, and then you can select components like this.
Right.
Okay, Vedat, I think we are out of time, and thank you all for today. Um, if there are any questions, please feel free to post it on the community, and we will try to respond to them.
Right. Yeah, John, if you cannot solve your problem, please write that to community post and we will happy to answer that.
Thank you.
Ankit, thank you.
Yes.
Thanks for the course
Yeah.
lesson.
Thanks everyone for
Learn a lot.
joining today. See you tomorrow. Bye.
Yeah, bye.